Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back. We are going to talk about bromination. Bromination is something we did in alkenes, and we saw that bromines had this triangular thing that blocked the top face, and then the other bromide attacked from below. And we would expect something very similar here. But that's not exactly what they believe is happening here. That may be one of the pathways, but there are other pathways as well. This is what they're observing when they have a dibromo attack. You have bromine adding anti, and that's something we saw with alkenes, except that we didn't have a pi bond. We had a sigma bond because we started with one double bond. This was your E, and then you really didn't get any Z. But here they do see a Z. So this mechanism is not very well understood, to say the least. Now, they have ratios showing that the E to Z is almost sometimes 62 to 40, which is pretty significant. So we can't say it's all anti-attack. There's something else going on, and so we're just going to leave it at that. So the proposed mechanism is something similar to what we had seen before, where your bromine forms a three-membered ring in the intermediate stage by attacking the pi bond attacking a bromonium. So this is something they had proposed earlier. However, this doesn't account for this. And in this case, you could only have another bromide attack from below. And it could attack here or here and roll over that other bromide to give you trans. So this could be how the major product is forming, but as I said before, it could be a 60-40, which is quite significant, and this may not be the only one, so there may be other pathways possible. What if you had excess bromine? Well, then it's going to do an addition here. You're going to pull this out. It doesn't matter here or here. They're both identical, and you would get a tetrabromo alkene. So here is your tetrabromo alkene if you had excess Br2. Now, this is in an aprotic condition like CCl4 or CH2Cl2. It's aprotic. So here you will get your tetrabromo. So this is only going to account for the E isomer. The Z isomer, we just don't know. We just, at this point, throwing our hands up and saying there's something else going on. We don't know what it is. All right, let's look at what happens if we modify our reagents a little bit. So here's the same bromine, but when we put acetic acid and lithium bromide, now you see a huge difference in the product distribution here. You're getting almost 99% of this. So it just goes to prove that there's so much more to actually learn about. And you can isolate this, and you can add chlorine if you want, or iodine. But if you, let's say, add bromine here, excess, you are going to get your tetrabromo here as well. All right, so tetrabromo is our end product. If you have excess bromine, it doesn't matter whether it's aprotic condition with CCl4 or with this, that's our end product if you had excess bromine. But if you had one equivalent, then you would stop at this. This is isolable. Then you can take this and go over and do other things with it, or just go over and brominate some more. All right, let's look at what would happen with bromine in a protic environment. So here you have an asymmetric alkyne, or a alkyne that has got two termini with different electronic properties. This carbon here has an R group donating electrons into it, so it's a lot more nucleophilic than this carbon. So electronically and sterically, these two carbon have different environments. Let's see what happens with bromine. So, well, if we propose something like this where you have a triangular bromine. And so let's look at a mechanism, possible mechanism. So you have a bromine that's going to attack that in a protic environment. Well, you need to have an electrophile. This is your nucleophile. In all cases, your alkyne pi bonds are your nucleophile. I haven't written it out here as much as I did in alkenes, but it's the same story. When you have pi bonds, there are your nucleophile. Pi is always going to start off with your nucleophile, so make sure your arrow starts from the pi. And then you can, attack a bromine, and the bromine here is very polarized, and so you can kick out one of the bromines. And therefore you have now a bromonium because these electrons were ripped off, and so you have a bromonium here. Cation, you saw this with mercury, you saw this with epoxides, you saw this with chlorine plus, bromine plus. So you've seen this triangular structure intermediate a lot. And here what we're saying is, in this case, you're going to have competition between bromide and water. Well, water is the solvent and it's surrounding this and also, probably hydrating this. So water has a better chance of getting in here and attacking. Now, it can attack here and it can attack here. Which of these carbons you think is going to be better for ripping off that bromine and forming a incipient or a temporary positive? This or this? We saw this before. Vinyl cations. When you have a vinyl cation, a secondary vinyl is better than a primary vinyl. So this is going to be the case here. We're going to have attack here because when you rip that off, you're going to have a more substituted vinyl cation. Exact same story. We're not changing the storyline here, except we are changing the molecules and doing pretty much the same thing here. And roll over bromide, and well, you might think, okay, now you have a pi bond. Why not attack that with a bromide now? Can we? Let's look at it. So here's your OH2, which is just, hanging on here. And I'm drawing this as trans because even here the majority was trans. So this was your major and this was your minor. So that was something new, something we didn't see when we did alkene bromination. When we look at this now, we are going to think, okay, we can attack this with another bromine. But before that happens, water, as I said, is surrounded by water. Water is going to get first dibs on this. It's going to go deprotonate that, and it's going to then give you an OH. And, well, what do you think? What do you call this, first of all? What is the name of this functional group? Enol, right? We've seen this so many times. As soon as you see a double bond and an OH attached to the same carbon, you know it's an enol. Okay, what does an enol do? Always, without any exception. It goes to the keto form. So again, we have water. Before another bromine can attack, this water is going to form a keto form. So here's your anion there, and this is going to be your oxygen that lost a lone pair and is positive and wants to be neutral. And over here, well, you're going to have something deprotonate this. Again, water is going to come in, deprotonate that, and you're going to get an H3O plus your carbonyl now with both lone pairs, so it's going to be neutral. And then you would have your CHBr anion. And the CH bromide anion can get protonated really quickly with any protons in the mixture. So that is going to come in. And even here we had an OH3. And so now when you come over here, you're going to get a ketone, and it's going to have a bromine right next to it. So it's an alpha bromo ketone. Anything that's next to this is alpha, then it'll be beta, gamma, and so on. We're going to talk a lot more about it later on. So you have a hydrogen here that comes from the proton. You have a carbonyl that comes from the water. And then here's the bromide that you added from your bromine. So these alpha bromo ketones are very useful in synthesis. And we're going to be doing a lot of that later. And this goes through an enol to keto mechanism. And because you have a keto forming, it's going to be a lot towards this side. Even though these are all reversible reactions, it's going to be more towards the keto, which is what's going to drive the reaction forward. This is almost like 190 kcal per mole for a keto bond. So there's a lot of delta H heat of reaction release, which makes it delta H, the enthalpy, very negative and high. And so the thermodynamics would favor the formation of these keto compounds and drive the reaction forward. So your K equilibrium will be a lot higher. All right. That's always the case when you have stable products. So that's bromination. Now, even here, if you isolate this and then you add bromine to this, even this is going to give you a very high percentage, 90% of this dibromo. So this is a really good way of brominating if you don't want to have mixtures. So what kind of selectivity do we have here? What kind of regioselectivities do we have here? Do we see any at all? In this case, in the first case, if you take this, really there is no regiochemistry because they're going to attack both these termini. They're pretty much the same. Even if you had a hydrogen, you would see the same kind of trend. So there's no real regiochemistry for that. So this reaction is non-regioselective. I have put it as stereospecific because the major product, after all, is E. But the minor product is a considerable amount. So if you had like a 60-40, which some people have proposed or obtained, then we have to really look at other possible pathways for that. Same here, this is going to be stereospecific because it's anti, but you're going to get bromination on both termini equally, so it's non-regioselective. So here the bromine, let's say, attacks from above, and the water is going to attack from below, that's the major, and so it is anti-stereospecific. Water goes mostly on the more substituted carbon. So therefore, there is regioselectivity here. It prefers this carbon over this. You don't get an equal amount of this and this. There's more of this than this. You may get a minor product from attack here, but the major product is attacking the more substituted carbon and giving you an enol that goes to the keto form. The only time you really get an aldehyde from an alkyne is from borohydration, because there the regiochemistry is different. It's anti-Markovnikov. All of the Markovnikovs put the keto on the more substituted carbon. Okay, so that's something to remember. There's one more reaction that I'd like to talk about, ozonolysis in alkynes. So now you're going to have ozone that is going to be the same ozone that we did in alkenes, and it's going to have a syn addition just by the way the reagent is. So it's going to be stereoselective. However, these are the products that they get. They get a carboxylic acid on one side and a carboxylic acid on the other side. So this is going to be very different from the alkene reaction that you did with O3-DMS. On alkynes, even if we try to get aldehydes, it's almost impossible because the aldehyde that's formed is then oxidized again to give you carboxylic acids. So now over here, this bond is completely severed, so you're breaking 1 sigma and 2 pi bonds, and then you're forming over here 2 sigma bonds and a pi bond for each one of these. So therefore, energetically, this would be favored, because sigma bonds release a lot more energy when they're forming than pi bonds. So yes, this reaction is really going to go. However, you will lose all your stereochemistry, and it's not really very regioselective because it's going to chop it and give you 2 no matter what you have on either side. It doesn't really matter what the R group is. If you had a hydrogen here and you started this off with a terminal, let's say you had a terminal alkyne like this, then once you chop this off with ozone, and then let's say you put in zinc, that's what they typically do, HOAC, you are going to get on this side carbon dioxide. So this carbon is going to go to carbon dioxide. You'll form formic acid, which then when you heat up gives you carbon dioxide, and then some H2O. So if you have an ozonolysis, you are going to get non-regioselective. However, it's going to be syn stereospecific at the beginning, just because of the way the geometry of the reagent is. It's going to only add syn. So it's stereospecific, but it's non-regioselective in both cases, whether it's terminal or internal. We didn't go over the mechanism of ozonolysis because that's really going to go over your heads. It's very complicated. All right, this is going to be regioselective and stereospecific. So it's going to be Markovnikov and anti. So whenever you get Markovnikov, as I said before, you would get keto products. Alpha bromo ketone. All right, guys, so we are going to look at some synthesis, and then we'll also do a wheel of reaction, a world of reactions here. You got plenty to go on alkynes and alkenes. I will see you in a bit. Talk to you soon, guys. Practice, practice, practice. If you have questions, just holler, and we'll get back to you with answers, hopefully. Bye.